Well, good day everyone. I'm Yuhao Huang from the National Taiwan University. Today I'm excited to share with you my recent work regarding the growth-dependent chiral exchange and demonstrate field-free switching utilizing the chiral exchange interaction. Here's today's outline. I'll first give an introduction to the interlayer Choleshinski-Moriya interaction, or DMI. I'll demonstrate how to induce this interaction in our lab and introduce measurement methods to capture it experimentally. And then we also capture the magneto-optical co-responses to an in-plane field to test the reciprocity of the interlayer DMI effect. Last but not least, harnessing the DMI effective field, we demonstrate how the PMI mechanization can be switched in a field-free fashion. And then there's our conclusion. So to start, DMI requires two factors. First is the strong spin-orbit coupling, and second, the existence of inversion symmetry breaking. One example is that interfacial DMI is often observed at magnetic multilayer thin films interfaces, for example at the PT Cobalt interface. On the other hand, theoretical calculations have revealed the possibility to extend DMI to a case of 3D, in which the antisymmetric exchange interaction is between two discrete magnetic layers, rather than a symmetry breaking in the plane normal direction. It is achieved by adding an in-plane symmetry breaking effect into the structure. So far, there are two strategies to generate the in-plane symmetry breaking. The first is the oblique technique, oblique sputtering technique, which induces a symmetry along the atom flow direction. The second way is to apply an external field during the sputtering process. It is also important to choose the anisotropy of the two magnetic layers, and some use two PMA layers. Others, including this work, use one PMA and one IMA in the orthogonal configuration. Next, we investigate the macroscopic consequences resulting from interlayer DMI. Since the interaction exists between two discrete magnetizations, we take analogy from the Zeeman energy and deduce the effective field experienced by the individual layers. And both effective fields depend on the other magnetization's direction, and thus the interaction is reciprocal. Note that the D vector, or the DMI characteristic vector, is well defined. It governs both the strength and direction of the interlayer DMI. We can make a brief comparison with the interfacial scenario right here. So sample growth and DMI measurement. In our experiment, an IMA Coulomb of 2 nanometers is first sputtered, then the PT4PT PMA stacks on top. The films are prepared with the rotor turned off, so it satisfies the wedge sputtering condition. The wedge mainly comes from the Coulomb flow, atom flow, and we expect the D vector we just noted before to be orthogonal to this symmetry breaking direction due to symmetry constraints. A field scan procedure is established here, in which a constant in-plane field H phi it fixes the in-plane IMA magnetization at the phi direction, while we simultaneously scans the HZ field to capture the hysteresis loops of the PMA layer. The results are shown here with our PMA IMA stack. The wedge stack indeed show a sizable shift in their switching centers, which depends on the phi direction, and we define it as H offset. This sizable offset is of stark contrast to our control samples, in which no shift is found regardless of the phi direction. Furthermore, we can see the clear sinusoidal form with regard to phi direction, which is a staple of antisymmetric behavior. Sinusoidal fit to the raw data suggests a HDMI magnitude of around 37 oersted, and the angle dependence is a perfect match for the argument that D must be symmetric orthogonal to the Coulomb target. So since the interlayer DMI is reciprocal between the two magnetizations, an effective field should exist within the IMA layer, and there are two scenarios here. The first, For a sample with a modest HDMI that does not overcome the PMA-HC, we initialize the PMA magnetization towards either positive or negative Z direction. We can see that in these L-mode field scan measurements, the IMA hysteresis loops are significantly shifted to either side, depending on the initialization. And this shows the effective field exerted on the IMA's antisymmetric origin. Furthermore, we can quantify the DMI interactions energy density with the following equation, and we can individually plug in the implan's effective field and implan's ferromagnetic data, and we can see that we found good mutual agreement between these two magnetizations, since it is to be expected, since they are both mediated by the same interlayer interaction. Well, in the second scenario, where the DMI field actually is higher than the HC, the implant field sweeping actually results in the both magnetizations switching coherently, as shown here. Not only that, the PMA magnetization switching polarity can be well determined and well dictated by the field scan sequence. So we suspect that if we use something like the implant switching to replace the implant field, perhaps the field-free switching of PMA is possible. So we now aim to achieve field-free switching. The DMI's characteristic D vector, let's say when we point to the -x direction, it separates the XY plane into two regions. When the MIMA or IMA magnetization lies within the first and second quadrant, the DMI field experienced by the PMA layer is positive, and when they are in the third and fourth quadrant, the DMI field is negative. Since, let's say, the implant magnetization follows a type-wise scheme, so for example, if we manufacture a 45-degree device on the XY plane, they can have their magnetization switch back and forth between these two regions that are stated here when the post-current change is signed. And when we compare this 45-degree device with, let's say, the 135-degree device, the nature of the implant switching is exactly the same, but the sequence of how the IMA magnetization traverses the XY plane is of exact opposite because of the geometry to be orthogonal. And if we utilize the opposite signs of DMI effective field, again, in the two regions, we expect possible field-free switching. So for both 45 and 135-degree devices, we perform current-induced magnetization switching measurements. And their PMA's field-free deterministic switching is achieved, as shown in the blue data here. We observe that not only is their switching deterministic, their polarity is of exact opposite. So it agrees with our prediction very well. Our model also suggests that the PMA and IMA should exhibit coherent switching, as indicated by the MOC results. And to verify this, additional current scans are performed, and we use this unidirectional magnetoresistance effect to probe the IMA's magnetization states. As we can see in the red data sets here and here, the critical switching currents of the PMA and IMA magnetization are of good match. So thus, we directly confirms coherent switching. We can thus say that, in a sense, the implant behavior is imprinted onto the PMA magnetization. And we note that since the implant switching has nothing to do with the D vector and is solely dictated by the implant current, the switching polarity does not change between these two 45 and 135-degree devices. And last, to exclude any other possibilities that can result in field-free switching, we also performed a current-induced hysteresis loop shift measurement. We found negligible current-related spin orbit torque exerted on the PMA layer. Thus, we can safely say that by harnessing the DMI effective field, a controllable polarities field-free switching is achieved. So here is my conclusion. So through wedge deposition induced symmetry breaking, interlayer DMI is generated between separate magnetic layers, and the DMI's characteristic direction can be controlled by the wedge direction and is universal. Both in-plane and perpendicular magnetic anisotropy layers' response to DMI are verified. And lastly, and most importantly, harnessing the DMI effective field-free switching with controllable polarity is achieved. And lastly, I would like to thank my advisor, Professor Qifeng Pai, for his supervision and contribution throughout this work, and also my gratitude to all my co-authors for their work and their advices. Thanks for listening.